Okay, everyone. So first off, your homework's now posted, and at the end of this lecture, you'll be able to do it all. And it's very similar to the examples we're going over here during this lecture. So what have we done so far? We've looked at multiple regression, mainly just descriptively. We just saw that when we add, for example, when we have two predictor variables, that we have a regression plane, not a regression line anymore. We pictured that. Now what we're going to do is we're going to do hypothesis tests, significance tests, to see if we have if our model, if r squared is different than 0, if our model has anything to it at all, we're going to look at the what's called the overall regression effect, and we're going to see if it's significant or not. And we're going to use an f-test for that. We can't use a t-test anymore because we can't boil it down to a single number. We can't a single difference. Okay, so that's what we're doing, and we're going to have the same assumptions that we had for simple meaning just one x predictor. One x predicting one y. Now we have multiple x's, multiple regression. We're going to do, it's the same assumptions. All right, so we're going to just go through them quickly here because we've already gone through them before. So we need to, the data has to have been collected using some randomization, either through a randomized experiment or through random sampling from a larger population. Or we have to, that's how we're modeling it. So we have to think about what that means. Then each of the predictor variables has to have a linear relation with the response variable. Okay, each of them should have a linear relationship. And then, what's next? To use our standard statistical tests, we also have to, that means to compute standard errors and to do hypothesis tests and confidence intervals. We have to make those same assumptions about the errors. What are those assumptions? That they are independent with equal variability across all the x's, and that they're roughly normally distributed. So we're going to be doing that same exact thing that we did before. All right, and so these are the same assumptions that we did before. So why don't we check them in the context of our example? But since that was last time, you might forget what our example was. It was that the 107 students, Stat 100 students, that were trying to predict their final exam scores based on their exam averages and their homework averages, that they were chosen from a large population of, let's say, 2,000 Stat 100 students. Well, that's what we're assuming. Honestly, it's not true. That's not how they were chosen. But, and this is often the case, that it's really not how they're chosen, but what we're thinking is that they're very similar to, that we can extrapolate to that larger population. We're imagining that they're chosen from that larger population. It would be best if they actually were. Okay? And then that the plots were the homework versus the final, and that was our x1, x1 versus y and our x2 versus y. Both show a linear trend, and they did. We already saw that. Remember, we looked back at that, and we saw that they did. I can show you if you want to look. Where was that? It was right here. They both showed a linear trend. What do I mean by linear trend? They didn't show a curvilinear trend like that or something. They showed a linear trend, so it makes sense to do a linear model. All right, and then, now, what about this? What about our errors? Well, before we can only check this assumption after we plot, we do the analysis and plot the residuals. So we'll examine how to check this assumption after we do the significance test for the overall model in the next chapter. Okay? We'll look at that later. So we're going to be checking these assumptions throughout. And what should we do if they're violated? Well, that's the subject of future chapters. We're going to be looking at what to do if they're violated. So if the random sampling is violated, like it was I'm imagining this, it really was violated. They were not actually chosen from a larger population. It happens all the time, and we try to assess how closely that the sample reflects that population we're trying to extrapolate to. For example, if your sample is all college students, you're not going to make inferences about all adults. But how about the linearity violated? Well, then what we're going to do, that's going to be later on, we're going to look at transformations of the variables to make them look more linear. That will be a section coming up after exam 2. And what if the errors don't have equal variability? Again, we're going to use data transformations to try to make them look more so that to make them equal variability along all values of x. And or we can switch to something called non-parametric methods, which don't depend on these assumptions about the distributions where the samples come from. And errors, what if our errors aren't normal? Well, this comes up in doing the hypothesis test. We can use something called re-randomization methods, which is coming up really soon. I think you're going to like it. It's another way to picture the randomness. Instead of imagining that they were chosen from a larger population, we're going to imagine that the scores were randomly, well, it will be much easier when we get to chapter 22. I'll explain it then. But it's a completely different way of thinking than doing these parametric tests, assuming doing a chi-squared or an F test. Okay, and then we could also do the data transformations, or we could use other non-parametric methods besides this one. There's lots of non-parametric methods, which we'll be discussing later on. All right, so that's where that's what's in future chapters. But for now, let's just go right to it and do a overall. Let's just do a significance test for the overall regression effect. That's what we're going to be doing here. And there's two types of tests we can do. The most commonly used one is an F test, but when n is large and the F distribution and the chi-square distribution are the same, so it's analogous to how the t when n is large and the z are the same. So basically, with large sample sizes, these two are going to look identical. All right, so what are we doing here? So remember what we just did before. We got this regression equation and we found some slopes that give the best fit, as far as minimizing the sum of the squared errors for our particular sample. Okay, but before we go much further, we want to check whether we should expect those slopes that we got to accurately reflect the population slopes, the betas, we'd get for the entire population of all 2,000 stat 100 students. Maybe they're just fitting some accidental features of our random sample. Maybe even our null hypothesis, that they're all equal to 0, that's going to be the null, would be except for the intercept. So that would be basically, if we're trying to predict the final, maybe just estimating the average final, just using the average final as an estimate. The average final that all the students got is the best we can do. Maybe the exam averages and the homework averages have no predictive value. That seems ludicrous in this example, but that's what that's the first step, is to see if the model has any validity whatsoever. And then from there, if it does, see which particular X predictors, whether it's the homework or the exams, or maybe both, have predictive value. All right? So now that we have more than one slope, our first step is to test whether any of the slopes in the model are significant. And that's where we're going to be doing this, this F test, or the chi-square. We're going to do that to test the overall regression effect. And then to test individual slopes, well, then we can go back to the t and the z. So if none of them are significant, there's not much point in exploring the model further, except in special circumstances. Okay? So first what everybody does is this overall regression effect. All right? So this is just the general idea. So you have more than, if it just looked like this with just one x, that would be simple regression, and we could use a z or a t-test, right? To test whether this is 0 or not, whether this x predictor has any. Now we've got more of them, so we can't do that anymore. And the null hypothesis is that all of these are equal to 0. Every single one of these slopes are equal to 0. And that's the same thing as saying that r squared is equal to 0, right? The correlation, multiple correlation coefficient is 0. That there's no correlation between what we would predict from this model and what the actual y variables are. Which is also the same thing as saying that our best predictor for y is the average of y. And that these x's don't help. Those are all saying the same thing. We already did that for the simple regression. When we tested the regression effect, we tested that when it looked like this, we tested whether beta 1 was equal to 0, which was the same thing as testing whether little r was equal to 0, which was the same thing as testing whether our y was equal to the average of the y's. And then the alternative hypothesis is at least one of these, maybe all of them, but at least one of them is not 0. Same as saying that r squared is not 0. Okay, so remember, all significance tests, all these hypothesis tests check how far away some random sample landed from what we'd expect in our null hypothesis, from what we'd expect. So we say, how far away did it land? That's what the p-value always measures, is the probability it landed that far away or even further. And when it gets too small, we reject that no. So with simple regression, we had the choice of either a t-test or an f-test. We could do an f-test, we did. It just gave us, it was like a two-sided t. And if n was large enough, then we could either use a z-test or a chi-square test. And the chi-square test gave the two-sided z. Now with multiple regression, we no longer have that choice. We no longer have the choice of using the t or the z. We have to use the f-test or the chi-square. And we've talked about this a lot. Why? And I'll just repeat it because it's important. Because we can't boil down the difference between what we observe and what we expect under the null to a single sign difference, like we could when we just had one slope. We could see how far that one slope was from 0. When with two or more slopes, we have to look at two or more differences. And some could be positive, some could be negative, others could be negative, so we can't just sum them up. We have to get rid of the sign first. So instead, we square the differences before summing them up. And both the chi-square tests and the f-tests are based on comparing sums of squared differences. Sums of squares come up over and over and over and again in all analysis of variance. All right? So that's the basic idea, and I'll just highlight it here. Okay, so I say here, and this is what we did before, if the sample size is large enough, we can use the chi-square test. Otherwise, we use the f-test. Okay, so basically, as n gets larger, as it goes to infinity, the f-test gets closer and closer to the chi-square test. So the f and chi-square are the same. And we did the same thing with, this is analogous to, as n went to infinity, remember the t got closer and closer to the z, so the t and the z are the same. And the reason most software programs will just show you the f and the t. The reason I'm showing you the chi-square and the z is because they're pedagogically much simpler. They're much easier to understand. So if in teaching statistics, it's useful to think of them this way. But the software, just because it gives slightly more precision, will usually just give you the f or the t. It won't give you this option. But these come up all the time, so I think it's nice to see the relationship. And you can estimate in your head better. Okay, with these statistics. All right, so now let's just do our example that we had before from last time. And we found this equation last time. This was the best, this is an equation for a plane. And it's the best fitting plane, regression plane, for our sample. And we got this R right here. We got that's a very high correlation coefficient, so it's likely to be very significant, right? That's a multiple correlation coefficient. That's the correlation coefficient between our predicted final scores from our model for all 107 people. If we put in for person one, if we put in person one's exam average, homework average, we get a predicted final, right? And then we'd compare that predicted final to that person's actual final. And so this R, this multiple correlation coefficient, says that we have a very good correlation, very strong correlation between our predictions using this model and the actual. So, but still, let's do an overall regression test anyways. But does it fit the population better than the null hypothesis that all these slopes are zero? The null is that knowing someone's exam average and or either one, or his homework average, either one, is no help at all in predicting the final scores. Common sense tells us to reject the null, and looking at this R value, it also tells us to reject the null. But let's see what statistics tells us. I mean, you can imagine if we only had 3 people, it could just be accidental fit, right? If we just had 3 people, we could get, but with so many people, it looks like it would be highly unlikely, common sense, to get that high in R squared, in R, right? Doesn't it? Yeah. Okay, so that's what we're doing. Now, here, remember that we've already looked at, this is the chi-square test statistic. We can do that first, and then we can do the F. All right? And we have a pretty big sample, so they're going to be very close to each other. And we'll see how close they are. We can use it for multiple regression, too. It's exactly the same thing. All we have to do is change these degrees of freedom. We already used this for the simple. And we said the degrees of freedom was 1. Now we're going to change it. All right. So let's just do the same thing we did before. So why don't we round this so it's easier? So we're going to say this is approximately equal to 0.62. Okay? So we'll just say 0.62 squared divided by 1 minus 0.62 squared. And then we're going to multiply it by what? Our sample size. And we get 66.81. So that's our chi-square stat. But now we have to adjust the degrees of freedom. Now for chi-square test, the degrees of freedom just depend on how many parameters are in your model. It's the number, remember, the degrees of freedom for the chi-square test is the number of parameters in the model minus 1, where the parameters include all the b's in the model, even the intercept. Okay, so how many parameters do we have in our model now? We have, there's our intercept, that's 1, 2, 3. So we have 3 parameters that we estimated. So I'll just say p equals 3. This has nothing to do with the p-value. This is the number of parameters. Okay? That's what we're looking at. All right, so how many degrees of freedom? Well, it's p minus 1, so it's going to be 3 minus 1. So now we have 2 degrees of freedom. Okay? Any questions on that? All right, so now we're just going to look at a chi-square table with 2 degrees of freedom. It doesn't have the F is stats more complicated because it will have the same degree of freedom in its numerator, but it's going to have one dependent on how big your sample is in the denominator. Just like the Z and the T has degrees of freedom dependent on this sample size, whereas the Z doesn't. And then when the sample size is big enough, they're the same. All right, so under the null, the chi-square statistics follows the chi-square distribution with p minus 1 degrees of freedom. It's written like that this little squiggly line means distributed as a chi-squared, and then you put the number of degrees of freedom in parentheses down here. So we can find the p-value. Okay. And by looking at these critical values, like here's a little tiny chart here, looking at these critical values that give you the null cutoff, and then the p-value is the area under the curve that's even more extreme than that. So let's see. So let's look at this. I think I asked an iClicker question about this, but here, let's just go zoom in a little bit. You can't even see this. All right. How big a chi-square do we need to reject the null at the 5%, at the 1%, and at the 0.1%? And what do you conclude? Well, let's do, well, what you want to do is you want to compare this chi-square. What do you conclude? We want to compare our chi-square stat with 2 degrees of freedom here, and that was equal to 66.81 to what? We want to compare it to the chi-square critical values for 2 degrees of freedom, and that's what this chart's going to show, at different alpha levels, okay, at different alpha levels. So you can look at this, and the 2 degrees of freedom is right here. So you're going to compare, so at 5%, at 1%, at 5%, 1%, and 0.1%, right? So, so at 5%, 5% means there's a 5%, that if we get a, if our chi-square stat is bigger than 5.99, we could reject the null and say that, what? Like on this on this particular curve, this must be a curve that doesn't correspond to 2 degrees of freedom, because if we go to 5.99 on this curve, it's got way more than 5% to the right of it. Do you see what I mean? So that wouldn't, it's not, this doesn't look like this. We can look and see what, let's fill this in, and then we can look at what the chi-square statistic looks like that has 2 degrees of freedom. All right, so at 1%, what is it? It's 9.21. So anything greater than that, and at 0.1%, it's 13.82. So let's go to, let's do an iClicker, and then we can look at the actual curve, so we could look at the actual p-value. All right, so let's do that. So let's go over here. And first, let's pull up a clicker question. And all right, we'll start this. And so just look at this. We're on page, go to page 98, where we're just left off, and you want to compare our chi-square stat to the critical values in part 3. That's what we just did. And what do you conclude from this? Just choose A, B, C, D, or E. I'll just give you 10 more seconds. Just make a choice. You'll go to minute and 10. Make any choice at this point if you haven't, because I'm stopping it. Okay? All right. And let's see what people chose. What happened to it? Oh, here it is. Let's see what people chose. All right, so I'm curious what people chose. So it's a toss-up between A and D. All right, so let's look. D is the correct answer. D is the correct answer, and let's see why. All right, so we know that our p-value is less than 0.1% because our chi-square statistic is greater than 13.82, right? It's to the right of that. So, and that's the cutoff to reject the null at 0.1%. All right, so what does that mean? It means maybe we should look at, for those of you who got it wrong, I think probably most helpful would be to actually go to, let's just go here to the chi-square distribution, and let's try it. So our degrees of freedom is what? 2. And what was our chi-square statistic? Do you remember? It was 66.8. And let's see what our 66.81. And let's compute the p-value. See how the p-value is really, really tiny? And our curve, so we knew we were to the right. The critical value was 13.82 for 0.1%. So we knew that there's only 0.1% of the entire curve to the right of 13.82, right? Right there. We can try, but ours, let's see, I'll show you. If you put 13.82 in here, let's try that, 13.82, and then compute the p-value, see we get about 0.1%. But we're way further to the right than that, so our p-value is less than that. Does that make sense to everyone? They're doing it as a decimal, right? So if you moved it over 2, it would be very, very close to 0.1% if we rounded. Does that make sense to everybody? You know what the chi-square statistic, and we're going to see this later, is centered at its degrees of freedom, meaning its mean is about its degrees of freedom. So if I put in the degrees of freedom here, this means you'd expect to see about 2 when the null is true. When the null is true, you'd expect to see about 2. Now you might say, well, why isn't that 0.5%? Why isn't it if it's the average? Because this isn't symmetrical. You're thinking of the median. This is the average. The median, this says, when you look at this, it says 36.79% is to the right of it. That's because it has this long right-hand tail, so the average is, the median would be, if I wanted to find the median, I'd put a 50 in here, and I'd compute a chi-square, and it's a little bit less than that. But that's not the average. I'm saying the average is around the degrees of freedom, okay? So as these degrees of freedom get bigger, like if we had 200, we'd expect a chi-square of about 200. And then you can see it's going to be close, it's more symmetrical, and it starts looking more like the normal curve. Every time you add a parameter, look, the chi-square, when it's just 1 degree of freedom, right, we say it's about 1 would be the average. It can't be negative, so it's about 1. That's the standard. It's like a normal square. You'd expect 0, but there's going to be variation around that 0, and it can't go in a normal curve. The average is going to be 0 because you can get positive and negative. Here you can't, so it has to. You're not going to get exactly 0, so that you're on the average for each. Think of it this way: for each parameter you have on the average, you're going to add 1. You're going to have variation of about 1. The chi-square is the sum of z-squareds. So if you just have chi-squared with 1 degree of freedom, that's 1 z-squared, 2 z-squared, 3 z-squared, etc. So if you have 100 parameters, it's like having 100 squared z-scores added together, each with about a variation of 1. So you're going to get a chi-squared, that will be about the average. So chi-squared, so think about it, if you see something much bigger than the degrees of freedom, you know to reject the null. Okay? We'll talk about that more, but that's the idea. So let's go back to let's just do our next. There was one more iClicker question. And let's do that one. So let's do the next one. And so what do you conclude from this? You know that the p-value is really tiny. So what do you conclude? Oh, duh, thank you. Some people don't, a lot of people in here don't have iClickers, right? Because there's a lot more people than are voting. Or didn't bring them or just are here, right? It doesn't look like there's only 94 people here. Does it to anyone? I would have you vote if you don't have an iClicker, but you can't. Okay, so, all right, so now let's see what people said. We're going to stop it. And let's see what people said. All right, C. Yes, C is the correct answer. Let's look why. So you reject the null and conclude either one of the slopes or both of them are significant. Why? Remember, the null is that all slopes are equal to 0. So rejecting the null means that not all slopes are equal to 0. That means at least one of them is. Not all, that means one of them could be, both of them. They're just not all equal to 0. So we don't know for sure. In fact, our next step would be, once you find that you have significance for the overall model, the next step, which is chapter 21, is seeing which slope. So we're going to look at the individual, we'll look at the exams and the homework, and see, and then do t-tests or z-tests on them just the way we did before. Okay? To see which of them is significant. All right, so let's go back to the notes. And now let's write up what we have here. So what did we do? So we compared ours to this at, okay, and what did we decide? Well, we saw that, compared to this and this, we saw that this, even at 13.82, it's bigger than that. That's bigger than that, so our p-value is less than that. So this is greater, that means it's further out, and so our p-value, so the p-value is less than 0.1%. That is at alpha equals, it's right here. If it's less than 0.1%, it's certainly less than the rest of them. Does that make sense to everybody? Okay. I should say, we could say at alpha equals 0.001. That's what we did. All right, and our conclusion is what? That the probability, should we write a conclusion here? And we're looking right here. This is all we're doing. It's not hard. We see that our stat is bigger than that. So we have to be even further out here. on the curve. And we conclude that maybe I should write it out because I think people have trouble with these p-values. Okay, so it means that the probability that we get such a big chi-squared, or even bigger, such a large chi-squared, that's huge, 66.8. Such a large chi-squared, or even larger, if the null was really true, if null was true, I mean, it could happen, but it's minuscule. We saw it. We saw how tiny, tiny, tiny it is so tiny, is less than 1%. We saw it's way less than 1%, is less than, I mean, less than even 0.1%. It's way less than 0.1%. So we reject that null and conclude that at least one of the slopes is significant. All right? So we conclude, we reject null, and conclude what? At least one of the slopes, maybe both of them are significant, and conclude that at least one of the slopes, at least one slope, maybe both, are significant. Does that make sense to everybody? It's just what we always do. Okay, so now what should we do? Now, let's just do the same exact thing using an F-test, and you can see the difference. Any questions so far? All right. So now our F-test is what? Oh, did I turn it? Are people still writing? Do you still want to? So now we're just going to do an F-test, and it's just we're going to get a p-value. Do you think the p-value is going to be bigger or smaller using the F? We'll see. All right, so I'm going to turn the page now. And so now we're going to do the same thing using the F-test. And you'll see how the idea is that using the F-test here, it's usually done using an ANOVA table, and we'll do that next. But it's easier to think of it as a slight adjustment of the chi-square. Remember, the F has the same relation to chi-square as the t does to the z. So how are they related? The key part of both statistics is this. You have the r squared divided by the 1 minus r squared. And the r squared is the strength of the model or our predictions, and the 1 minus r squared is the strength of the errors. Okay? Now, the chi-square curves are based on the normal curve, and the F shares this analogous relation to the t. The F-test gives you slightly more precision. The p-value is always slightly bigger. You need more evidence to reject the null, but the difference is negligible with large samples. All right? So let's look at our two stats side by side. So let's look at this. So here, what we're doing is basically we're measuring the strength of our model, r squared, and then we're taking this 1 minus, and this is the strength of our errors, but we want the average. Each little point, each person in this sample is going to have an error associated with them, right? It's going to have an error, like how far they are off that regression estimate. So this is like the average of the errors. You divide by n. That's the average of the errors. And so, but then, when you simplify it, it comes up here in the numerator. All right? And that's a chi-square. And then you look at a different curve depending on how many parameters are in your model. Each time you add a parameter in your model, you'd expect the chi-square to be centered around the number of parameters. So it's a different curve. Now let's look at the F curve. Okay, you see it has r squared over 1 minus r squared. Now instead of dividing by this n, so here's your n, instead of dividing by the n, you subtract off the number of parameters. It's the same thing you did with the t and the z. You subtract off, there's just one parameter, and you say n minus 1. You divide by n minus 1. Here you're dividing, or the square root of n, here you're dividing by n minus p. You're subtracting off as many parameters as are in the model. And again, this ends up here in the numerator. So this ends up here in the numerator when you simplify. All right, so that's one difference. But here, there's another difference, and that's that no matter how many parameters you have in the model, you don't divide, you don't do anything. Instead, you adjust your, you shift your curve over. But here, this is your model, okay? So this is the strength of your model, and each time you add a parameter, you can fit the model better. So you can think, okay, I'm going to have to divide by the number of parameters here. Here we don't do it, we just, I'll explain later, but we just change the shape of the curve. But here we divide by the number of parameters. And so this, basically this numerator, so you end up with two sets of degrees of freedom, p minus 1 in the numerator, which is the same as, these two are the same degrees of freedom here. This is p minus 1. And then you have another set right here. All right? But even though it's in the numerator, when you simplify, it's in the denominator. So that's what it looks like. And what this does is it centers F. Doing this centers, remember chi-square is centered around its degrees of freedom, p minus 1. Well, when you divide by p minus 1, this centers F around 1. That's what this part is doing. It's to center F around 1. Because that's really a nice statistic, to be centered around 1 when the null is true. And that's what this part's doing. It's just a different way to compute things, so that's why that's happening. All right, so now, let's see. So now let's just remember what our model is here, and we're going to do this. So let's just copy it down again. We had a predicted final, predicted with a little hat over it. And we had, I'm just copying from the previous page, 11.91 is our intercept, plus 0.1641 times the homework scores, plus 0.5824 times the exam scores. And we had n equals 107, all right? Now, we're going to assess the whole fit of this model. The only thing we're going to be using to assess it is we're going to use this, our n, and that's going to feature in right there. And we also need the number of parameters. It's going to be this 1, 2, 3. That's 3 parameters. And we need we have to be given r squared. And r squared, that's from the previous page, was what? That's just what we had here. R is 0.62. Okay. So you need to know that too. R is equal to 0.62. Okay, so now we can compute F. So let's just do that. And F is going to be equal to just r squared, the same thing we did before, over 1 minus r squared. But now, instead of multiplying by 107, we're going to multiply by what? 107 minus 4. 3, minus 3. There's 3 parameters, right? The parameters up here, 1, 2, 3. So it's going to be 107 minus 3. And then we're going to divide by, so that would be just a slight tweak that would make F a tiny bit smaller, just like the T is a tiny bit smaller than the Z. But then we do this other big tweak, and we divide it by the number of parameters minus 1 by the degrees of freedom. And that makes going to make F statistic about, look, we're going to be dividing it by 2. Compared to the chi-squared, we did that. That's what we did with the chi-squared, right? And we got 66.8. Now, that's not going to make much of a difference, but when we divide it by 2, we're going to get like half of that. So we end up getting 32.47. All right? So it looks really different. See, here we had 66.81. So it's basically half as small, and then it's adjusted a teeny bit smaller because we're multiplying by 104 instead of 107. All right. So how many degrees of freedom in the numerator? In the numerator, don't get confused, even though this looks like it's going to be 104, that was the simplified. In the numerator, we want this. That's 3 minus 1, which is 2. I'll just highlight it because it has to do with the model. It has to do with the model, not with the errors, that parameter. How many parameters are in your model? That's the numerator. Your numerator is always your model, the strength of the model. Just when we simplify it, of course, that becomes the denominator. And same here. So then in the denominator, what are your degrees of freedom? Well, in the denominator, your degrees of freedom, that has to do with your sample size. It's 107 minus the number of parameters. So it's this. That's the denominator. Okay, that's how you figure it. That's the numerator. Even though people always get confused because you're computing it this way. That's just the simplified version of it. Any questions so far? Okay, so now, because there's 2 sets of degrees of freedom, this is more complicated. All right, look, because the F has 2 sets, you need a separate table for each p-value. Here's the table for p equals 5%. These p-values are nothing to do with parameters. This is p-value, okay, the probability. All right, so this is for this. Same as alpha equals 0.05 or 5%. That's just this one. So where do we look? Well, our degrees of freedom for the numerator is what? 2. So that's here, the numerator. So you want to look in this column. And then we have 100 degrees of freedom for the denominator. Degrees of freedom 2, they call them. That's 104. So it's like right in between 60 and 120. So we can look at these two. And now remember, we're trying to assess whether our F ratio is bigger than these. Well, if it's bigger than this one, it's going to be bigger than this one. So you're going to just compare what we got, the F stat, people call it ratio lots of times, the RF ratio to what? We want to compare it to the critical value, the cutoff, for the curve that has 2 degrees of freedom in the numerator and 104 in the denominator. But we don't have that on this table. We want to do that. We want to compare it to that. And that, yeah, I don't know why that happened. Hold on. Okay. And that is equal to what? Well, do you think it's, okay, so the critical value at alpha equals, it's going to be, see, it's going to get smaller and smaller and smaller. Should we see what it is? Let's go look. Anyway, we're going to compare our F ratio, which is 32.14. It's going to be greater than whatever that is. It's certainly greater than 3.15. It's going to be somewhere between 3.15 and 3.07. I looked it up and it's 3.84. But it's bigger. We don't have to be quibblers about this because clearly it's bigger. It's going to be between those two, and the upper limit is 3.15, so it has to be bigger than that. So the p-value has to be less than 1%. Not less than 1%, less than 5%. All right? We can figure it. This is 3.8. I looked it up before. But if you wouldn't have that on your exam, so what would you do? I would just take the bigger one, because if it's bigger than the bigger one, you know it has to be somewhere in between there. So looking at this chart, you could just compare it to 3.1505. Does that make sense to everyone? Okay? All right, so let's go look at the F curve. And I said the F curve is centered at 1. So why don't we look at the F curve over here? And let's go to the F. Whoops. Let's go to F here. And so what we're going to do is the degrees of freedom in the numerator is 2, and the denominator it's 104. And our test statistic was huge. It was 33. We'd expect to see 1. It was 33.47. So it's going to be a tiny, tiny p. But what I want you to wonder about is, well, you probably won't be able to tell. It's going to be slightly bigger than the p-value we got using chi-squared. But they're both so tiny, it's hard to tell. Look at that. It's so ridiculously tiny, you probably don't remember what it was before. But it is a little bit bigger. So look at that. That's ridiculously small. Because as I said before, it's going to be centered around 1. So if you look around 1, that's not the median, but that is the mean. It's approximately the mean. And if you get more degrees of freedom, let's just say 100 here, and then you can compute the p-value, the F, again, is centered, becomes more normal looking, but the difference is that it's centered around 1, and the chi-squared is centered around its degrees of freedom. Okay? So let's go back to the notebook and talk about that. All right, so here's our two statistics that we have. And again, they look very, very similar. Here you have this n here, and here you have the n minus p. So you multiply, and here you have this p minus 1 that you're going to be dividing. See, you're dividing it by, right? And so this degrees of freedom and that degrees of freedom are the same, but then you have this extra set of degrees of freedom that have to do with your sample size. Okay, so they have different numerators and denominators. Why? The denominator is easy to explain. It's analogous to the z and the t. Remember, the f-stat, just like the t-stat, is the statistic we use when we have normal distributions but don't know the standard deviation of each variable but have to estimate them from the sample SDs. So we make two adjustments. We make SDs a little bit larger, right? We've done this before. And then we square them to get the variances. So the difference of the factor and the variances is 107 over 104. Okay, so that's, here you have, in this case it would be 107 over 104. See, because we had 107 here, and here we have 104. Now, we use the F curves instead of the chi-square curves. And unlike the chi-square curves, there's a different F curve for each degree of freedom in the denominator. The F curves, just like the t, have a fatter tail compared to the chi-square and the normal. So you need more extreme evidence to reject the null. So the p-values using F, the p-value is the area in the tail, right? The p-value using the F is greater. It has a fatter tail than the p-value using chi-square, right? Same as the p-value using the t is greater. So than that using the z. How can you, so the f and the t, think of it this way, are fat in the tail. Fat in the tail. You can remember that. The f and the t are fat in the tail. So the p-values using the f and the t are going to be bigger than using the corresponding chi-squared and z. You're measuring the area in the tail beyond us. So that's an easy way to remember it. So that's why you need more extreme evidence to get that same little tail. You need to go farther out with an f and a t. Okay? Does that make sense? So p-value using f, it's the same p-value using what? T, is also greater than the p-value using z. It's the same thing. All right, so that explains the difference in the denominators, and it's just totally analogous to what we already talked about. But what about the numerators? Why are they so different? In fact, let's look at them. The numerators. I'll just, all right. So the numerators. In fact, the chi-square stat is, remember, it's centered around its degrees of freedom, so it's really its degrees of freedom times the f-stat numerator, p minus 1 times that. In this case, it's going to be 2, because it was 2 degrees of freedom. And that's because, watch, we're dividing the f by that. So multiply it by p minus 1, you'll get your chi-squared. So why? So this is just this is history. This has nothing to do with statistics. Why? The difference in the numerators is conceptually meaningless. It's just a historical accident of who decided what names to write down, really. Fisher, the f is named after a guy named Fisher, that's why it's called f, decided it would be nice to divide by the degrees of freedom in the f-stat, since it makes typical f-stat values about 1 when the null is true, regardless of the degrees of freedom. I think that's really nice. I like what Fisher did. I think that's really nice to have the same, you always know it should be about 1 when the null is true. Pearson, on the other hand, who discovered the chi-squared distribution, decided not to divide by the degrees of freedom. So the chi-square stat's typical values when the null is true is the number of degrees of freedom. So the difference between the chi-square and the f is completely, and the real difference, the statistical difference, there is a difference, is completely analogous to the difference between the two. With large n, they're the same. But the z and the t look the same. They have the same statistics. The reason why they look so different, why people don't even realize they're the same, because the f-stat is usually so much smaller than the chi-square stat, because you divide by the degrees of freedom. They just happen to look different because of a historic. You know what I don't like about it, coming from a philosophy background, is that usually these type of things are corrected so that you can call things by a particular name and they have the unity seen in the name. You don't have all different, it makes the job of philosophers is to try to unify things and to try to. So statistics is a very new science, relatively speaking, and they haven't done that yet. I think eventually, hopefully they will. Or maybe they never will, but it makes it hard to teach. All right? So I just want you to understand they're really very similar. They just look different. Okay, so here is the idea that the f-stat, I said, is about 1. It's really degrees of freedom in the denominator over the degrees of freedom in the denominator minus 2, but it's about 1, and the chi-squared, the mean of the chi-squared is its degrees of freedom. So this is what you should really remember here. So when the F stat, remember this, so when your F stat is much bigger than 1, or your chi-square stat is much bigger than your degrees of freedom, you know to reject the null. That's the idea. So you can get eyeball it and know when to reject the null. All right, so now we can do this same example with an ANOVA table, just to get you familiar with what you'll see in printouts, because they'll always give you this printout, this ANOVA analysis of variance in all the software. So let's just look at it. We've talked about it before. All right, so let's set up an ANOVA table just like we did in part 1. So the ANOVA table always breaks down the sum of squares total into 2 pieces, right? All right, so let's just do this same example. Fill in this, all right, so what do we have? What are we given? All right, so let's say we're given that the standard deviation of the finals is that. We're given that n is equal to 107 and r. This is what we know. So we could also fill out this table and arrive at the same F stat. All right, so first, the sum of squares total. So if we know the standard deviation is that, the sum of squares total is going to be, first of all, it's just the numerator. You're not dividing by n, so you have to 100n times 10.27 squared. That, okay? And that's 11,285.6 squared points from the average. Deviations from the average, that's what that means. The sum of squares total, these total, how much the variation of the y's. This is the variance times n. All right, so we'll stick that right here. That's what this is. And we're going to break that variance of the y's into 2 parts. This is called the sum of squares total, and we're going to break it into 2 parts. The part due to the model, and that's r squared times that. That's the proportion of that due to the model. And then due to the error is 1 minus r squared times that. So let's do that. And so we'll just multiply this by, basically, this is all we're doing. Don't get distracted. We're just saying, okay, you have some data here, right? Right, the total. And we're just breaking it into 2 pieces. The model, we've done this a lot, plus the error. That's all we're doing here. And this is like your signal, and this is like your noise, right? Now, the data, the way we're describing the data, is subtracting. If everybody had the same final score, there'd be nothing to predict, right? We're trying to explain variation around the average. Why some people have high finals, some people have low final scores based on, we're building a model to describe that. So variation, and we're looking just at the variation, the sum of the, we're looking at the deviations from the final, from the average final, and then we're squaring them. And then we're adding them all together. So this, all right? And we're saying, okay, that we're taking into 2 pieces, right? We're breaking it into 2 parts. The part, this is the proportion of that that's explained by our model, and this is the proportion of that that's explained by our error. So that's what we're doing here. Okay, so there we have it right here. So now we're just going to take, if we know what r is here, we're just going to say 0.62. I'm just going to approximate that as 0.62. Okay, just because it's easier. And look what I wrote down, sorry. 0.62. All right, squared. And times our 11,285.6. And then I'll just say 0.62 squared. 1 minus 0.62 squared plus 1 minus that times 11,285.6. And when I did that, I just got 4,338.6 66.18, and when I did this, I got 6947.42. Okay? When you square this, you get about 38%. So 38% of this is explained by the model, and 62% is left in the errors. So let's fill that in here. So this is 4338.18. They have to add up to that. All right, so now we've broken it up into those two parts, and then the degrees of freedom for each. Remember, this is the error, so the total degrees of freedom, remember, is n minus 1, 106. Where am I getting this from? This is, I'm using this. All right, so that's where that's coming from, and basically that's where this is coming from. And then what do I do for the error? It's just going to be 107 minus the number of parameters, which was 3. We have 3 parameters here. So that's 107 minus 3, so that's 104. This is really connected to that mostly. And then for our model, we know we have what? The number of parameters minus 1. So this is for our numerator, basically, and this is our denominator, approximately. And then what do? We just say, okay, we're going to divide our sum of squares by however many parameters minus 1 in the model. So I do that, and I got 2169. You're going to get exactly the same thing we got before. And now you're going to divide this by the error degrees of freedom, and you get 66.8. And then you take the ratio of these two, the mean square model over the mean square error, and that's 2169. It's just what we did before, over 66.8, and we'll get the same exact thing we got before, 32.4. Okay. One thing I should show you too, because it's often, I should show you what, if you take the square root of this, take the square root of the mean square error. It's called the root mean square error. If you take the square root of that, that's called your root mean square error, and that's also called the standard deviation plus of the errors. We looked at the standard deviation of the errors, and this is very similar. It's a tweak on that. The standard deviation of the errors with the square root of 1 minus r squared times s dy. Well, this is the square root of 1 minus r squared, the square root of 1 minus r squared. We take this divide. It would be, if we divided by 107, it would be exactly our standard deviation of the errors. It's just a tweak on that. All right, so you'll see that in the homework. We'll explore that a little more. And so basically the idea here is, that we have the F is figured as the ratio between the mean square model over the mean square error, which is r squared times SST for the model divided by its degrees of freedom over 1 minus r squared times SST divided by its degrees of freedom. This is p minus 1. This is n minus p. So then when we do it, the SSTs cancel out, and you get just r squared over 1 minus r squared times this factor, n minus p over p minus 1. So we'll get the same thing. All right. Okay. So we should just look at the summary and do, I know you're getting tired. You have a long weekend. Maybe we should do this. It might help you, though, the last 10 minutes. I hate to go the whole hour, but I think this might tie things together. All right? So let's look at the last page. It's the summary of Chapter 20. And you'll be able to do all your homework, and I think it will, after you do your homework, I think you'll understand it better. All right. So, so here's our unifying theme. It's separating the signal from the noise. That's what I'm trying to get a unifying theme going here. We're just comparing the model to the error. Okay, and so that's what we're doing here. And here's just what I said before, this. So, and these are test statistics that we use to find p-values to answer the question, is our sample signal big enough to reflect a real signal in the population, or is it just due to sample variation? So that's what we're using. Notice, the bigger n is, sorry, that's a typo. Notice, the bigger n is, like once you simplify it, I love this form of it, because once you simplify it, the bigger your test stat will be. When n is bigger, you have bigger sample size, chi-square will be bigger, and so will f. That makes sense, since the bigger your sample size, the better you'll be able to detect a real signal in the population. A signal that's really there if you have a bigger sample size, and that shows up right here, because you're multiplying by n up there. So if you had data on the whole population, you could detect the tiniest little, any signal, no matter how small it is. So this really shows you that the bigger n is, the stronger your test statistic is. So that you'll have better evidence to hear a signal. This is, all right? Now, so the significant, for the, okay, so here, so I'm just going to give you two practice examples. These are two separate examples. This is practice example 1, and this is practice example 2. They don't have anything to do with each other. All right, so let's just look at the first practice example and see if we can do it, and then we'll do the second one. They're just really easy math, easy ones. All right, so this is your first one. So what are you given? You're given all this, and I want you just to compute the chi-square and f. Okay, so you're given this model, and you're given this r, and you're given that n. So first compute r squared in. Okay, so r squared, I'm just looking here, is just, you're just going to square that. So it's 0.01. And 1 minus r squared is just going to be 1 minus that, so that's 0.99. All right, so now compute your chi-square statistic. So chi-squared is equal to, it's just going to be equal to 0.01 divided by 0.99 times what? Well, you just look right up here and you multiply it by that, times 100. And I got 1.01, okay? Now, do you think it's going to be significant? No. How many degrees of freedom are there? How many degrees of freedom? You have to think, remember, chi-squared is going to be much bigger than its degree. How many degrees of freedom? Well, how are we going to figure that out? We just look here, and we see 1, 2, 3, 4 parameters. So it's going to be the degrees of freedom will equal 4 minus 1, which is 3. Okay? So we have that, those degrees of freedom. All right, there's the 4. Now, I don't think it's going to be significant, because when the null's true, it's going to be centered around 3. Yeah?
What's the value at the end?
This?
No, in the model.
That's the error. Oh, thank you. This is error. If I had put a little hat over this, then I could have erased that error. You can either say you have a prediction, or you can say you have your y plus error. Two equivalent ways of writing it. Sorry, good question. Yeah, if you don't put that little hat up there, you have to put an error attached to it. But if you make a prediction, you do make a prediction with this, but if you don't write that, then you have the error. Good question. Any other questions? Okay, so now those are equivalent ways of writing it. Now, compute f. So let's do the same thing, and let's compute f. And by the way, I got a p-value here of 80%. I looked it up and I got a p-value of 80%. That's huge. You're not going to reject the null. Remember, it's going to usually be 3, so you'd have to get much bigger than 3. Now let's do f. So we'd say f equals the same thing, 0.01 divided by 0.99. And now what would we do? Instead of 100, what are we going to do? 100 minus what? 4 parameters. So that would be 96. And then what do we have to divide by? The number of parameters minus 1. So that's 3. And when I did that, I got 0.323. So look, because we have degrees of freedom 3, this is going to be about a third the size of that. And here, by the way, the p-value is going to be bigger. It's 80.87. All right? How many degrees of freedom? Let's write down. The degrees of freedom 1 in the numerator is what? 3. The same as this. These are the same. The degrees of freedom 2 in the denominator is going to be 100. That's the 100 there, minus 4. So that's 96. All right? Any questions on that? And I think do you want to save this one for next time because it's getting so late? We can do that. We can save it for next time. I think you'll be able to figure out how to do this. Okay. Oh, by the way, if you want to do this on your own, I just want to show you. You can't do it yet. I have to give you some more information. So if you wanted, I'm just going to give you more information. Because you'd probably look at this if you tried to do it. You can't do it. Now you could do it. I'd have to give you R and SDY. We'll do it next time. I said I just have to give you R, I say is 0.5, and SDY is 10. We'll go over it next time.